Good morning. This is my video submission for the end semester examination. This video will answer the sixth question out of the overall set that we received. So, uh, I'm Anand, and now I'll just state the question here. This question states that we have a non-homogeneous second order linear ODE given here, and we need to model this mass spring system such that uh, okay, there's no condition. I'm sorry about that. So the question has three parts. One of them is the first part of this question is to give a real life scenario where this kind of a differential equation might have some kind of an application. So what we have on the right hand side is the Dirac delta function. It's a unit impulse function that we use to signify a strong impulse at any given instant of time. So we can model a hammer blow in this case. So a normal mass moving about a pivot or a reference point and hinged to a spring, sorry, and suddenly we subject it to some kind of a hammer blow, if you refer to what our textbook says, and suddenly this system is moving in a completely different direction. So this is what this might model. The second part is to use our intuition to sort of draw a solution which may or may not resemble one. So mine is, so this is a mass spring system, and the question deals with the acceleration of the system at given point of time. So I assume a sinusoidal motion that is until say time t is equal to 3 pi. So yeah, we'll have a normal sinusoidal system. I'll just sort of, yeah, sorry, yeah, we'll have a normal graph here, that is. So at time t is equal to 3 pi, my system suddenly gets a pretty sort of strong impulse, momentary force acting on it. So the acceleration in so the FBD in this case is changes. So all of a sudden we have let's just say a point of discontinuity here before it begins again. Or rather, executing with a different amplitude, my system executes itself until it dampens itself again to this current amplitude. So this is what I assume. So I will just draw this a bit more clearly, just for support. I'm thinking of something like this, that is until a momentary force acts on it, and suddenly we have motion with varying amplitude, and it's sorry, this is not true, sorry, and suddenly just it sort of moves to its natural frequency and comes back to this motion at later time. This is what I assume at my motion. So this is my intuitive solution for this. Sorry, now for the third part I need to solve the ODE. So So I need to first of all form a subsidiary equation. So I will do that, and there's no shifting in this case. So we'll apply the initial conditions here and get the answer, that is, so this is true, and we get e to the power minus pi, or rather, just a minute, e to the power minus of pi s. Since the question here sort of acts at time t is equal to 3 pi, so we make similar adjustments here as well. So this is my substitute equation. So y becomes somewhat equal to this now. So we don't see any shifting here. So this can be written as therefore we can write by t as the inverse transform of this function. So on top we have the exponential factor. So by the second theorem of shifting, I can write my final solution as the Heaviside function of this transform times sine of 4 times minus 3 pi. Okay, a small change here. The question actually had a factor of 4 here. I'm so sorry about this. Just a minute. I have to make a change here and here. Okay. So this is what we get. Sorry. So since sine of 4t minus 12 pi, which is a factor of 2 pi, I mean it does not really change, so we can write the solution yt is equal to 2u times minus 3 pi times sine 4t. So we don't have any change over there. This is the correct answer. So when I draw a graph of this now, till time t is equal to 3 pi, we'll have essentially no motion. So this is like this. After that we have a normal motion wherein we have with amplitude of 2 on both sides of the x-axis. We have this, and then it continues its sinusoidal motion till infinity. Now we don't have any dampening in the initial equation, as you can see. So this essentially continues till infinity. So this is the equation of motion, the correct equation of motion. So as compared to this, what I had drawn, this looks like the more accurate version. So what we have here is correct equation of motion. Now to spot the differences in this, obviously we don't have any motion here, so in accordance with the first theorem of shifting, we will not have any motion in this case. Now the reason this might be true is because the spring mass system remains in equilibrium, and the net, since we don't have y double prime, we should not have a y either. After this we have the unit impulse acting here, and since the change in momentum is finite, since the interaction of the force of the impulse is short, the motion that it leads is essentially sinusoidal, and we get this motion. So this is what it is. Alright, that's it. This is the end of the question. Thank you for your time. Stay.